Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 129, some root to leaf numbers. After that, we'll go over two actual variants of the original question that Meta asks. It's more likely you'd be asked the OG problem, but sometimes the interviewer will introduce some mathematical twists that make it a bit tricky. We'll go over them. Great, let's read the problem statement. We're given the root node of a binary tree where each node's value is a single digit from 0 to 9. So taking a look at our tree real quick, we have a 3, 6, 1, and a 4. Furthermore, we're told that a root to leaf path in the tree represents a number. What's this mean? They don't really explain it. Looking at our example here, it's a sequence of nodes specifically from the root node to a leaf node, like this one right here, such that we concatenate the digits along the way to build a number. So here we'd have a 3. At node 6 here, we concatenate the 3 with the node value of 6 to get 36. And lastly, at the leaf here, we concatenate the 36 with the node value of 1 to get 361. No, it's not actual algebraic addition where we add 36 and 1 to get 37. Rather, think of these numbers as strings that, when added, we get 361, thus a concatenation. And as a quick note, if it wasn't clear, a leaf node is defined as a node that has no children. So node 1 is a leaf and node 4 here is a leaf. What we want to do is return the total sum of all root to leaf numbers. Referring to our example here, we'd add up the built number of 361 plus the number we'd build at this leaf node, which if we concatenate the 3 with the node value of 4, we get 34. Putting those together, we would get an ultimate answer of 395. That's our answer, and that's what we return in our function. Okay, so that's the overview of the problem. To solve this, we can try to simulate the exact workflow we just demoed. But to do this, there are two outstanding questions I have. One, how do we traverse the tree in the first place? And moreover, two, how do we actually build the number to each leaf? Namely this 361 and the 34. Okay, so for the first question, we observe in the quick walkthrough that we visited the current node before going to its left or right subtree. As we saw, when we were at the root node 3, we built our number to be 3 before recursing to the left subtree. Then at node 6, we processed that current node to get the 36 before recursing to its left subtree again to node 1, where we processed that current node to get 361 before recursing to its left subtree, which by the way is null pointer. That's a base case. We just return and backtrack at that point. That makes sense to me since we'd encounter each value in the right order to ultimately build our number. Alright, so we reach into our pocket of tree traversal recursive algorithms and we pull out pre-order where we process the current node, then the left subtree, and on the backtrack the right subtree. We also have in order where we entirely process the left subtree first, backtrack to the current node, before finally going to the right subtree. Lastly, we have post-order, where we visit the left and right subtrees in that order before finally processing the current node. Which one is the only algorithm that processes the current node before going to either subtree? Well, by definition, that would be pre-order. Here, specifically, after we visit the current node, we recurse to the left subtree rather than the right subtree first, but it doesn't really matter. Again, as long as we visit the current node first before recursing downwards in either direction, we'll be set up to build our numbers correctly. Now that we clarified that, let's address the second question. How exactly do we build the root to leaf numbers and work our way up to the 361 and the 34? Let's go through our example, but more in depth. Well, first things first, let's initialize a variable called curSum to stand for current sum to 0. And you may have guessed this will track the current sum in our path so far. And for visual purposes, I'll write out the current sum value, but not the actual variable name since it takes up a lot of space in our diagram here. Okay, let's start our pre-order CLR tree traversal and process the root node, node 3. It doesn't take a genius to know that the current sum takes on the value of the 3. Let's make another if statement here. Are we at a leaf? No, it has 2 children. Next up, our pre-order traversal instructs us to recurse to the left subtree. That's what we'll do to go to node 6 to be processed. At node 6, we have a current sum of 3 and a node value of, again, the 6. How do we concatenate the two to get 36? Well, we put our mathematical hats on and realize we want to reserve 1 decimal place for the 1 singular digit of 6, thereby shifting the 3 from the units place to the tens place. Therefore, what we can do is multiply our current sum by 10 to get 30. That way, we can simply add the node value of 6 to our 30 to get the desired 36. Amazing. Let's write that down. 36. Next question, are we at a leaf node yet? Nope, node 6 has a left child of node 1. We move on in our pre-order, where we must go to the left subtree to that node, node 1, to be processed. Here, let's try to apply the same math. We have a current sum of 36 that we passed, and we want to concatenate the node value of 1 to ultimately get 361. Since we want to reserve 1 decimal place for the 1 digit of 1, we'll shift our 36 from the tens place to the hundreds place. To do that, remember, we multiply this by 10, shifting it to the left once to get 360, add the 1, and you get the 361. As the way this works, remember, we're confined to numbers from 0 to 9. Multiplying by 10 will do the trick every time. Great, so we got the 361. We asked the same question, are we at a leaf node? Finally, yes we are. That's a base case. And that's because node 1 has no children. We'll add the number we built of 361 to the same variable as before, total sum. And as a quick optimization, we don't have to actually traverse to the left and right subtree of node 1, because by definition of a leaf node, there are no left and right subtrees. Great, let's finish this walkthrough. We return as another base case since we reached a leaf, and we backtrack to node 6, where we're now told we have to go to the right subtree. Let's do that. But hold on, it's an old pointer. That's another base case. We return from there. And since we've exhausted both subtrees, left and right, we'll backtrack to the root node, node 3, where, yet again, we're told to go to the right subtree to node 4. We pass in a current value of 3 that we want to concatenate with the node value of 4 to get the 34. One last time, you multiply 3 by 10, simply add the 4 to get 34. Now that we process that, as always, we'll ask the question, are we at a leaf? Yes, it doesn't have a left and a right child. That signifies to us we've fully built a number. Let's add it to our total sum. What do we get? We get the same answer as last time, 395. We return this. This is our answer. Now, in retrospect, I don't know if you caught it, but we technically didn't go through the very first iteration where we had a current sum of 0 that we defaulted it to, and we visited the initial node, the root node of 3. We'd get a concatenation of 0 plus 3 to get 0, 3, which really is just 3. Does our formula work? Amazingly though, the maths out. Anything multiplied by 0 is 0. So if you add the 3 to it, you just get the same value, 3. So everything works out. Okay, the time complexity is big O n, where n is the number of nodes in our tree. We process each once. And the space complexity, in the worst case, is big O h, where h is the height of the tree. A quick explanation, since this is a recursive function call, in our example here, we'll hold at most 1, 2, and then 3 stack frames in our stack of the 3 nodes, which is equal to the height of 3 nodes. Hence, it's big O h. Okay, fantastic. Let's write the code up. All right, let's ready some variables. We have our total sum, remember, which we default to 0. In the end, that's what we return, so let's do that before I forget. We also want to track the current sum along any given path of our built number. We can't modify the original signature function, so let's write a helper function to take in both of these parameters. We'll call it the same name, sum numbers, but it'll be overloaded with the root, but also the total sum, as well as the current sum. On any given node that we're on, what happens if we're at a null pointer? Well, if that's the case, we simply return, that's one of our base cases, we backtrack. Otherwise, we're at a node with an actual value. Remember our equation. We update the current sum by multiplying it by 10 and then adding the current node's value. After this, we ask the question, are we at a leaf node? And that means the left child would be null pointer and the right child would also be a null pointer. If so, we've fully built a number of a root to leaf sequence. Let's add it to our total sum like so. Of course, this means there's no left or right subtree. We can just backtrack and not traverse those null pointer children. After we've processed the current node, our pre-order traversal instructs us to go first to the left child, and we'll pass in our two parameters here. And on the backtrack, visit the right subtree. And similarly, we'll pass in the same parameters. Lastly, let's not forget, let's call our overloaded function with the expected parameters. And there you have it. There's the implementation. Okay, things are going to get a bit trickier. Let's move into the variant. In the case that Meta decides to mix things up for you, they may ask this variant, where we're still given the root of a binary tree, but each node value can range anywhere from 0 to 999. In other words, we're not limited and confined to only digits 0 to 9. So in our example here, sure, we can still have digits like 3 and 2, but we can also be given larger numbers like 79 and 111. All the other requirements stay the same. We still want to return the total sum of all the root to leaf numbers. Alright, so what changes in our implementation? Thankfully, not too much. It makes sense we'd still use the pre-order traversal algorithm where we visit the current node and then the left subtree, and then on the backtrack, the right subtree, because we want to encounter each node in a top-down fashion. But that said, along this example path here, the way we built the number changes ever so slightly. For instance, when we're at the root node with a current sum of 3, and our pre-order algorithm tells us to visit the left subtree to node 79, we want to concatenate the current sum of 3 and the node value of 79 to get 379. But how? If we tried the math in the previous problem, we'd multiply our current sum by 10 to get 30, and then we add the 79. That, however, gets us 109, not the 379 that we need. Let's take a step back and isolate our bigger example into a smaller, more manageable one to try some different mathematical examples and see if we can observe any patterns. Okay, here it is. Here's our very contrived hypothetical example. Don't worry about the original problem for now. We'll get back to it. And yes, node 7 is quite wide. Don't judge it. Let's say, for example's sake, we had a current sum of 3 and we're on node 7 with a value of the 7. Our output then should be the concatenation of the two to get 37. This is reminiscent of the OG problem. We realized that we should multiply the 3 by the 10 to get 30 because we wanted to reserve one decimal place for the single digit 7. That way we can add 7 to the 30 to get the desired 37. Great, that works out. Now, let's say our node 7 was a node that had a value of 79. Just like our original example, by the way. The concatenation of the two, the current sum of 3 plus the 79, should yield a 379. We realize we need to multiply the current sum not by 10, but by 100, because we want to reserve 2 decimal places for the 2 digits 7 and 9. And if we do that, we get 300. And we can add now the 79 to 300 to get 379. Okay, we're noticing a pattern here. Let's do one more example. Now let's say our node is 799. Our current sum is still 3. We add it with the 799. That gets us 3,799. We realize we multiply the current sum not by 10 or 100, but by 1,000 because we want to reserve 3 decimal places for the 3 digits 799. And if we do that, we get 3,000. You add the 2 and you get the new sum of 3,799. Okay, let's formalize this logic in code speak. Let's take this example right here. How do we know to multiply by 1,000? Well, if the number of zeros we need correlates with the number of digits the node has, in this case it's obviously 3, then here's what we'll do on any given node. We'll initialize a local variable called places for decimal places and initialize it to 1. And then we'll enter a while loop to keep dividing the current node's value, 799, by 10. All the way until that node value reaches 0. And each time we do divide it by the 10, that's another unit place we have to reserve. Let's multiply our places variable by 10. That brings us to 10. Okay, 79 is not 0 yet. Let's divide it by 10. Once again, we get 7. In doing so, let's multiply our places by 10. That adds another 0 to get 100. 7 is not 0, so let's do it once more. We get 0. We successfully divided by 10 though. Let's add another 0 here. And we stop our while loop because we hit 0. Therefore, this tells us we'll multiply the 1,000 with the 3 to get the familiar 3,000. You add the 799 and there you go. You get your answer. That's the logic. There's a more mathy solution that uses the log function, but I don't expect anyone to recall pre-calculus class. Now let's roughly go through the rest of our original example. I won't be showing the nitty-gritty details because it's quite obvious now that we've established the necessary steps. We were on node 79, remember, where we build our current number to 379. We recurse to the left subtree, there's nothing there, so we backtrack. Therefore, we'll go to the right subtree to node 111. You add the current sum to the current node's value, and you get that built-in number. We realize we're on a leaf node, so we'll add that number to the same variable, total sum, to get so far a sum of 379,111. Great, it was a leaf node, so we backtrack. Since we've exhausted both trees on node 79, let's backtrack to the root node, where we go to the right subtree. What's the concatenation of 3 and the node value of 2? That's 32. When you look at that, it's a leaf. Let's add that to our total sum, and what do we get? This very large number as our answer. And just so you know, don't worry, the summation of any built number will fit inside a 32-bit integer. There's no need to worry about overflow. The time complexity is the same as the OG problem. It's big O(n), and the space complexity is big OH, where H is the height of the tree. Alright, the code isn't too bad. Let's start. The only thing that changes is the logic to build our number. Line 6 will change. Remember, instead of the hard-coded 10, because we may be given larger numbers, we multiply it by a local variable called places. And for this to even work, let's initialize that very variable. We initialize it to 1. Next, we're going to keep dividing the current node's value by 10 until it reaches 0. Let's make a quick copy of the current node's value. We don't want to mutate it. And then enter that while loop that as long as the node value is higher than 0, we'll do two things. We'll divide it by 10. And if we did so successfully, we'll multiply places also by 10. And when we're done, we'll multiply the current sum by the right factor of 10, whether it's 10, 100, 1,000, and so forth. The rest of the logic remains the same, and that is it. Fantastic. Sadly, the next variant is more tricky, but really just more random. Let's take a look. Okay, so the second variant is comparatively more complicated than the first variant, but only because Meta tosses in a lot of seemingly random requirements. Let's read the problem description and see what is different. It does start out normally. We're given the root node of a binary tree that contains digits from -9 to 9. Each root to leaf path in the tree represents a number. Okay, brace yourselves, here comes the weird part. A number whose sign should be negative if there's an odd number of negative nodes in its path, and conversely, that number would be positive if there's an even number of negative nodes in the path. These are known as a negative and a positive path, respectively. Furthermore, the sign of a node should not affect the root to leaf calculation other than the consideration of a negative path. Wow, that was a lot. That's overwhelming. There's not much to actually explain in this variant since all Meta did was complicate the problem with more rules. It's better to go through an example and just show how everything works and going over each additional requirement one by one. Alright, here's our example. First off, it goes without saying, we'll be reusing the same pre-ordered tree traversal of CLR, where we'll recursively visit the current node before visiting its left subtree, and then on the backtrack, the right subtree. Now, as to how we progressively build our number, the logic changes drastically. This requirement right here tells us we need to disregard the sign of nodes in our root to leaf calculations. Therefore, when we kick off our tree traversal and process the current node, the root node, we'll follow the same formula from the OG LeetCode problem, but with a small modification. We'll take our current sum and concatenate it with not -1, but the absolute value of -1 to get 1. Remember, we want to ignore signs in our math. And by taking the absolute value of a number, we guarantee that it's positive. Okay, great, so we got the built number of 1. Let's write that down. Lastly, we ask the same question. Are we at a leaf node? No. This node has not only a left child, but also a right child. Okay, now that we're done with the current node, let's go to the left node now and repeat that logic. Let's speed run this a little bit because I don't want to get redundant with the math. What's the current sum so far of 1 times 10 plus the absolute value of -2, which gives us 2? We get 12. We've successfully ignored the node value's sign. Let's denote our sum here. Are we at a leaf node yet? Still no, it has a left child, where according to our algo, that's where we're going next. We have a current sum of 12. We multiply it by 10 to get 120, and then we tack on not -9, but the absolute value of -9, which is 9, to get 129. Are we at a leaf node? Finally, yes we are. Now here's where another requirement comes into play. This number that we built will be negative if there's an odd number of negative nodes in the path. So in retrospect, looking back at our path, how many negative numbers did we encounter? Here's 1, here's 2, and here's 3. There were a total of 3. Since 3 is an odd number, it means we have an odd number of negative nodes in our path. We have a negative path. Therefore, what we'll do is just multiply the 129 by -1 to turn our built number into a -129. And like before, we'll add that to our total sum variable, which will ultimately return, and we have 129 so far. And as to how the negative number will be introduced into our logic, we'll just pass around another variable, perhaps call something like num negatives, which represent the number of negatives so far in the path. And that anytime we process a current node in our tree traversal, if it's a negative number, we'll increment that variable. So at the root node, we had 1 negative. At the next node, we have 2 negatives. And then finally at the leaf, 3 negatives. Cool. With the workflow ironed out, let's finish this example. This is a leaf node, so we backtrack to its parent node, where we'll try going to its right subtree. It's a null pointer though, so it's another base case. We backtrack from there, and then we backtrack to the root. We'll now visit the right subtree, because that's what we're told to do, to node 4, where we pass in the negative variable of the 1 and the current sum of 1. What's 1 times 10 plus the absolute value of +4? Well, that gives us 14. There's no side effect, obviously, when you use the absolute function on a positive number. It remains the same value. Let's write 14 here. Is a node value of 4 a negative? No, it's not, so we don't increment our negative variable at all. It remains at 1. That -1 in this current path is the only negative number. Last question we ask, are we at a leaf node yet? No, it's not. It has a child right here. We're done with the current node, so CLR tells us to go to the left node now, where we pass the current sum 14, as well as the negative variable of 1. On node 5, what's the current sum so far of 14 times 10 plus the absolute value of -5? That would give us 145. Let's write that down. Is -5 a negative number? Yes, it is. We increment the count of the number of negatives to 2. Are we at a leaf? Yes, we are. There are no children. Therefore, we'll ask this question. Was this root to leaf path a positive path? or a negative path? Well, we have an even number of negatives this time, which means we have a positive path. The 145 that we built remains positive. Let's add that to our total sum, which gets us an answer of positive 16. That's the answer, and that's what we return. The time complexity is the same across all problems. It's big O(n), and the space complexity is big O(h). Okay, let's take a look at the code implementation. First thing we'll do is initialize our num negatives variable to 0. This represents the number of negatives in our root to leaf path so far. Let's introduce it as a new variable, the fourth one. Let's change our helper signature and also pass it into our pre-order invocations for the left and right subtrees respectively. Great, let's demolish this code right here. We're back to only having single-digit values. Our equation on line 6 here slightly changes. We're given values -9 to 9, so we can hardcode the 10 again. But when we add the current node's value, we want to make sure we take the absolute value of it to make sure it's positive. We want to disregard the sign in our math, remember. The next question we ask is the current node value negative, as in below 0? If it is, we'll increment our num negatives variable like so. After that, the last question is, are we at a leaf? If we are, we need to determine if our built number should be positive or negative, depending on if we have a positive or negative path. We can easily do this with our num negatives variable that we introduced and mod it by 2. And if there's a leftover, that means we have an odd number of negatives. Our sign will be -1. Otherwise, it'll be 1 for positive. We'll multiply our current sum, the num we built so far, with that sign and add it to our total sum. It's a base case, so we return. And there you have it. It's unfortunate to see companies try to obfuscate already tricky tree problems, but it is what it is. At least we're better prepared now. All right, good luck on your interviews. And if you learned something today, please make sure you like, comment, and subscribe. Thanks for watching.